Okay, guys, welcome back. Based on today's weather, I believe I made a mistake when it came to the United States. I think I want to go back to Africa. Yeah, this is too cold. I know many people like to see the white color outside. For me, it's like wow, too much. I mean, yeah, it's fun to have a snow for 1 2 days is okay, but not for the entire life. Yeah, so just watching, see, it's too cold outside. Anyway. I'm keeping complaining. So, first of all, I really apologize for being late for a few minutes. I got stuck in a meeting with the department, so I had to attend that meeting and didn't realize that the time is almost over. The start must be start. Anyway, last lecture we went over the symmetric encryption scheme, right, in general. So we started looking at the modern symmetric encryption scheme. We looked at the Feistel structure driver, which just to remind you what we did quick here. Then after that, we kind of jump to see what the DS and etc. So that's the Feistel network of cipher. As we mentioned last time, it's like a design model. So that means in this case, I use this one in order just to get used as a template. So there is no encryption scheme called Feistel. Okay? So the structure here, it's easy. Simply you have the plain text, you divide this one into two halves, left and right, then you're gonna perform the operation, okay? So the encryption process, as we saw last time, uses the Feistel structure, which consisting of what? Multiple rounds of processing what? The plain text. Each round consists of substitution step followed by the permutation. So that's what we did for each round here. You take the right half, pass to the left, and the left half is going to be perform some operation that's like XOR with specific function, and you're going to perform, let's say, the function is going to take two input, this what's it called, the round key or the sub key with the right half. Then after that, produce the result, and you have to switch or exchange this one to the other side. Perform this operation over and over. So we have a multiple rounds. This is the structure for the encryption. Okay, for the decryption we said, the process can be like what? Is almost similar. The only difference here, instead to start we have the keys, K1 and K2, you have to insert K, for example, whatever, how many rounds? You have N, then I'm going to use Kn, then here the Kn minus 1, and etc. So I'm going to use the keys in the reverse order. Okay, remember, we do have only one master key, and we're going to use this key in order to produce a subkeys. Okay? So this one allow us in order to what? The last final permutation or change that we have here, or swapping, let's say swapping is better, between an L and S, allow me to use the exact structure, the exact piece of hardware. The only difference, just I want to specify what's the input. Instead, it's going to be the plain text, and going to be the input, the ciphertext, and then provide you with the keys with the reverse order. So I'm going to use the exact procedure, the exact software, and the exact hardware that we have. That's the reason why we have the final permutation here, or the final swapping. Make sense? Then, in order to come up with the exact implementation of Feistel's the structure or the scheme, it depends on what? It depends on what you're looking for. And we're gonna see as example in DS, we're gonna see how exactly we're gonna assign or specify, for example, some feature. For example, what's the block size for the Feistel network? The block size is going to be 2W. Now, if you want to use this one in specific encryption scheme, you have to say, for example, what the block size is going to be. For example, 64 bits, 128 bits, and etc. Okay, so the block size is going to be different. I mean, it depends on your implementation. It depends on your whatever. Encryption scheme that you're going to use based on the size. You're going to design based on the size, Feistel. So it might be 64. It might be 128 bits. This one, if we have a larger value, that's going to lead us to have more diffusion, right? What do you mean by diffusion? Just to remind you, here's going to be influence of one plain text, or change in one plain text, is going to spread over many ciphertexts. That's the meaning here, yeah, to make it diffusion. The larger plain text that you have, the larger diffusion you can end up. Because you have many bits you can play around. The key size, what's the size of the key? Right now we said the size of key may be X, B, bits, or whatever. Now we need to specify the exact size of the key here. And you keep in your mind, the larger the value that we have, maybe going to lead to have more confusion. Yeah? Confusion just techniques that just remind you with the definition to make sure, or ensure, the ciphertext gives no clue about the plain text. Hide the relationship between the ciphertext and the key. So if you have a larger key, then you get a chance to have a more confusion. And also, the larger key, we're going to see that later, it's going to allow us, or it's going to be provide us with the resistance against the brute force attack. Brute force attack, when you try to find, try all the possible combination, all possible key. If you give you, for example, 5 keys, you choose one of them, so it's easy. You need to just to test 5 keys, right? If you said the keys is 1 billion keys, oh, that's hard. Because like the sample, I'm going to choose one random. Good luck to find which one I choose. You see that the larger, they make it resistant against the brute force attack. How many rounds do we have here? Generally speaking, the rounds, it depends on, for example, 16, 14, whatever. It depends actually what we try to achieve here, okay? So keep in your mind, more number of rounds is going to provide more secure system because you're going to perform this one for a long time, yeah? So you're going to achieve more diffusion and confusion. But the problem here, at the same time, more rounds is going to mean at the same time inefficient, slow encryption and decryption process. Because, you're going to perform, for example, 5 rounds. If you compare the time that's spent to perform 5 rounds with the time that you're going to perform for encryption, decryption, and the number of rounds is 16 or more. So you see that it's going to spend a long time, right? In this case, in the second case. Number of rounds, again, in the system depends on the efficiency and the security trade-off. Yeah? We're going to take a look at this one later. More details, we'll talk about the DS and the AS. Subkey generation algorithm should be complex. You need to come up with these, we use a 5-standard structure. You could have a complex mechanism in order to generate the subkeys using only master 1 master key. And also you need to come up with a round function that should be complex, not simple one, which achieves substitution and permutation. That's what we need to perform here. Of course, another factor when you try to use, implementation using the 5-standard structure, you need to come up with a fast encryption, decryption, either it can be in software or hardware. Yeah, good. Let's take a look now, one example here. We are going to take a look to the data encryption standard, which is one way that block cipher that operates together based on the 5-standard structure. So we're going to take the 5-standard structure, which will do minor modification, and say, this is our data encryption standard. The size of the message is, first of all, the size of the message is 64 bits. Okay? And the size of the key, or the length, this is the length of the key is better. The length of the message, 64. And so it looks like you have the input. You have the message, something like this. You have, for example, DS. So you have here, for example, the plain text. The plain text, 64 bits. And the key is going to be 56 bits. Produce the same ciphertext, the ciphertext is going to have 64 bits. So this is the minimum. So in order to perform encryption, you have to provide me with a block, and the size of each block will be 64 bits in order to perform encryption using the data encryption standard. Okay, it's when you start looking or working with the data encryption standard, people were like not happy with the process how they select that. It's suddenly in 1977, National Bureau of the Standard. Now they call this one the National Institute of Standards and Technology, NIST. They said, okay, we need the encryption scheme to use for public. Then the IBM said, oh, here you go, we do have encryption scheme. No one knows what's going on, how they choose this one, what the design model, why they choose, for example, some parameter, as we're going to see later at that time. Okay? Everything is hidden. And no one can participate except the IBM, researcher and somehow the National Security Agency. Okay? The problem with that, the first, at the beginning, the IBM says the key size is going to be, for example, it's going to be 128 bits. But once the National Security Agency gets involved, the size of the key has been reduced up to 56 bits. You see, we reduce the size of the key. If we reduce the size of the key, that means the system is going to be less secure, as we're going to see later. And also there is some, let's say, the way that how can we choose the Sbox, we're going to see later, some features inside this DS, it's not clear at the time, okay? So that's why the people said, okay, it looks like there's something fishy. And if you're interested to learn more about this one, you can click over this link to read about more about the legacy of the AES. I think the Congress made the investigation in 1975 or something like this. I didn't remember that. Not 85. The investigation result is secret. No one knows that. But as the summary, they said, I will conclude that there is no malicious activity from the National Security Agency at the time. No one believed that. Anyway, so let's back to the system itself. So this is how it looks like. We have the key. So when you have the block cipher, when you talk about the block cipher, you have to be because what the encryption scheme, the data encryption standard. What the input size of the message, 64 bits. What the size of the key, 56. Okay. Then what the size of the ciphertext is going to be similar to the size of the plain text. Okay. And here it looks like we have what? Initial permutation, final permutation. Then we're gonna perform this one encryption in 16 rounds. Yeah. Yeah, I know my voice is annoying. Make sense? So this is the structure. Okay? So we do have the first thing that come to your face, the first step, you're going to do initial permutation. Then after that, after you've done encryption, you're going to do the final permutation. We do have 16 rounds, the number of rounds 16. And you have one key for every single round we need to provide, the subkey. So similar to the structure of the 5-star network, but here we need to specify more. For example, what do you need to perform inside the encryption for each round? All the rounds are going to be perform the exact operation. Okay? That's why we call these operations going to be identical. Good. The security depends on what is called substitution box. We're going to show you later. Okay? And each of these boxes. No, we are going to talk about this one later. But what they said here, they choose list number of rounds. They say there's shortcuts somehow. Yeah. So let's say that let's be secure and let's choose 16. Yeah. In order to have like balance between or trade-off between the let's say the efficiency and the security. Okay. Yeah. So it's fixed. It's standard 16 rounds for the DS. Okay, good. So let's take a look at the structure. So I'm going to take a look first at the times, go over these steps. Okay, I don't want from you to memorize, but I wanted to show you that we have like a model 5-star network. We take this model and we come up with an encryption scheme. Actually, we didn't do that. They did that for us. Okay, so actually the initial permutation and the final permutation doesn't, don't have any cryptographic significance. They use them in order to facilitate, at that time they use with 8-bit, based hardware to fit the data. So that's why it looks like the way how to connect the input to the data, and with the time they keep it as with the standard here. So initial permutation, the final permutation at the end doesn't really, add to the security here. Okay, so if you take a look with the encryption here, over the step for every single round, we still have the left and the right. Right? We divide this one the same as 5-star. We perform the exact operation. The only difference here, we are going to in the 5-star, they didn't specify what the f function is going to be. Right? Now we need to come up and tell me what the actual f function looks like. Here we have numbers. Now we see that the size of the message is 64. We divide this one 32, 2 halves each 32, and then we're going to perform the operation. One thing, if you notice here, for the f function, it's going to be like 2 input, requires 2 input, right? Require, for example, the Ri, let's say -1, or the value of Ri, and it's going to have the key I, -1, yeah, the brief value and the subkey. The size of the key starting, we're going to talk about this one later with more details, but the key is going to be start with the 56, and we end up, we have here, going to be 48. Okay, it's going to be somehow operate or processing with the right half of the message with 32. We're going to take a look with more details, see how it looks like on the side. Then after that, the left and the right is going to be swapped. So it looks like it's similar to the 5-star with minor variation. Okay, let's take a look now with more details here. As you mentioned, the left and the first, we do have the initial permutation, and after you're done at the end, you're going to perform the final permutation. Okay, we have the last swap, then we have the final permutation. the initial and the final permutation, as you mentioned before, is like doesn't add to the security. It's just at the time, because they use different hardware. You work with a 8-bit based hardware. This is the mid 1970s, I mean. So yeah, maybe you're born at the time. You're not. Anyway, so the way how to connect the wires. Okay, so let's take a look one at a time. What's inside this? The initial and the final permutation here, if you take a look here, it looks like we have like a straight permutation boxes where they're going to inverse each other. So when the first one, you take the message or the input message, and you have to connect this one, permute it based on this table. So those tables are fixed. They are not changed. Those tables are inverse to each other. So for example, let's take a look. You have a message. You take a look at the first one here. Take the first, if you have the message 64 bits, right? From 1 up to 64. First take the bit number 50. Put the first one. 58. Then after that, the next, whatever, so let's say 54, 58, yeah. I need new glasses. Actually, it's new class, but getting worse. Put the first bit here. Then after that, take the bit number 50 and put it here. Edit it. Right? When later we finish the encryption, now we need to reverse the operation. Whatever you have the bit 50, first bit here, move it back to the location 58. Whatever you have in the second bit, it was the bit 50, move it back to the bit number 50. So that's why we have one table and we have another table. We use this one in order to say, we call this one straightforward. I mean, permutation box. Make sense? Just for the wiring here. Okay, you see that number. So if you take a look, where we're going to have for the first bit in the message, the first bit is going to be go to the bit 40. That's what we have here. Put it here. The bit number 2, we want this one into the bit 50. You see that in the 50 here. If you check this one, 40. Where's the bit number 2? Sorry, it's going to be bit 8. Sorry, it's going to be here. And it's it. So we have a specific box permutation, use them in order just to reconnect the data. Make sense? So again, it's not related to the security, the way how to use the hardware at the time. They must connect it like this. Okay, no question, jump to the next one. So we're done for the initial and the final permutation. Now let's take a look here what is going to happen here. All of them is going to be straightforward, right? The only difference here, we need to see what's going on inside this function, the round function. Okay? With the value here, which is the main component of the DS function, encryption and decryption, or they say system, or crypto system. You see that inside this one, we have many functions. The first one, you're going to do expansion. Why expansion? Remember, if you take a look at the function here, or the input here, we're going to process 32 bits with 48. So what I'm going to do here, I'm going to expand the number 32 in order to increase it to be 48. Then after that, we can process them. So the first one, expansion. Yeah, increase the size here. So we have 32 input. It's going to be 48. We're going to show you how can you perform that. Especially we have like a table we can follow. All of the table are fixed, okay? Then after that, the only difference is the key and the message, of course. Then after that, we're going to perform XOR with whatever the output with the expansion with the key. Okay, the subkey. Then after that, we're going to perform, let's say, what is called the Sbox substitution. The input is going to be for each box 6 bits together and produce 4. Then after that, perform the final permutation. This is going to be happening inside the F here. So here, if you take a look here, that's the F function. Okay? Let's take a look one at a time. What you have in the expansion here, just very quick here. The expansion is going to do what? Expand the mask. So you have a table. So we see that some bits is going to be what? It's going to be, actually do this one, expansion and permutation. Permutation is going to permute to do what? It's going to change the location of the bits, scramble them within, together, yeah? The first bit maybe is going to be jumped to the second or the fifth, and etc. We keeping doing what here? We do a permutation, doing diffusion, right? So we have 32. I have a table, straightforward table. It's going to be expand, so there's some bits going to be occur twice. Because here we have 32, I need to, from 32 end up we have 48. So we have 16 bits is going to be repeated twice, based on this formula, based on this table. Okay? When you have this table here, I'm expanding, and you see that, for example, the bit 1 is going to be appears twice. You shift it a little bit, then take the last bit, put in the first one. I have another diagram. I think we can maybe simulate this one something like this. So the output something like this here. You have, for example, the first bit 1, 2, 3, 4 here. You take the first bit, it'll be bit 32, it's going to be here. This is the output. Then after that, well, just take a copy for these bits here. Yeah, actually this one is going to be here, and this is bit number 5 is going to be passed here. So that's why we have here 32, 1, 2, 3, 4, and we have 5. Yeah, so yeah, 4 will be here and here, and 6, 7, and etc. Or you just follow this one. You take the output is gonna be what? 48 bits. The first bit, take the whatever you have the input 32, the bit number 32. Then after that, one to the first, the second, the third, the fourth, the fifth. Then after that, repeat the 4th bit twice. Continue in this one, based on this formula. Okay? And remember, you're gonna perform this one multiple times. Every time, every single bit is gonna be somehow change the position. Alright? Because now when you're gonna perform this operation, produce whatever the result is gonna happen, gonna end up we have like 32 bits. Now we're gonna perform the next operation here later after exchange, of course, you're gonna perform the expansion again. Yeah, so it's gonna be, it looks like if you change one bit, this bit is gonna be affect the change at the end. These are not for the expansion or the function, and gonna be maybe changed at these 2 bits. Okay, and each of them is gonna be affect another 2 bits and etc. Yeah, I looked outside, everyone sliding in the snow. I don't know, these people, my neighbors are, they are crazy, but I mean, too cold. I mean, for me, I'm not gonna get out until this, the white stuff is gonna be disappear. Anyway, so we did the expansion, based on that straightforward. Then now we did XOR, yeah, 48 with 48 bits, yes. It's easy, bitwise, that means bit by bit. Then after that, now, I do the third one at the third step. This is the Sbox. This is the very important, step here. One thing about the XOR that we did before, we call this one white now. Usually, this is the only position that we're going to use the key. Usually, we take the message XOR with the key in order to make it more, to hide the original message and the key. We call this one the key whitening. Okay? This is the Sbox with the very important one. We do have here 8 Sbox substitute or box or substitution tables. They are fixed. They are different. They are not the same. Okay, but if you ask anyone at the time why they choose these numbers, no one knows. At that time, in 1970s, when they came up with this algorithm, the only one knows the IBM and the NSA. Okay, after 15 years, people knows why these tables are designed like this. Okay, so again, right now we don't know how they choose that. The only thing they said, those are the 8 tables that we use. So you take first all the first 6 bits. You have here 48 bits, right? Take each the first 6 bits and use the Sbox one. This Sbox one have substitution table, have specific numbers. Okay. Then the next 6 bits, we're gonna use the different substitution box or Sbox 2. Has different structures. Though these numbers gonna be different from table to table. They are not unique. There are 8 different, substitution. If you take a look here, you have a column, and we have a tuples or rows. The intersection between the tuple and column is gonna tell you what the value for each tuple. It's gonna be permutation from 0 up to 15. Each of them from 0 up to 15. Okay, how they do this one, we don't know at that time. After 15 years, there is a researcher from Israel. Okay, they found a way to break the DES, but because of the way that these Sboxes, are designed, so the DS was, robust against this kind of attack. You see that? So after 15 years, okay, when these guys published the paper, the IBM and the NSA said, yeah, we know about that 15 years ago. Why didn't tell us? No one cared. That's why people, they more suspicious. Okay, it looks like they're aware of this kind of attack. That's why they designed their, Sbox like this. I believe if you change any of these numbers, the system is going to be vulnerable to that kind of attack. You understand this one, what's going on? Okay, so that's why the way they design Sbox and tie against that attack. Oh, after 15 years, they know what's going on. So this is the most important thing. What I want from you to know here from this part, if I give you a Sbox, whatever S1, S2, or S3, I want from you to find out how can you use Sbox in order to produce a result. Remember, you're going to have 6 bits at input, and you're going to produce 4 bits. Okay? For example, if we give you, for example, this number, let's say 1, 0. Let's have another one, okay? How about you have 1, 1, 1, 0, 1, 0. Okay? 1, 2, 3, 4, 5, 6. Then you need to apply the Sbox in order to produce the result. How could you do that? You take the first bit and the last bit. The first and the last bit, okay? This one we have 1, 0. 1, 0 is gonna tell you, for example, which row you need to choose from this table. So 0, 1, what's the binary representation, decimal value of 0, 1? In order to compute the decimal value, you know the first, if you have many bits, the first bit will be to the power 0, to the power 1, to the power 2, to the power 3, right? So it will be 1, 2, 4, 8. If you have 1, 0 here, so it looks like the decimal number value is going to be 2, right? So here it's going to be 0, 1, 2. So we have find the value equal to 2, right? Or in this case, we can find whether it's going to be which, the first, the second, and the third, and etc. So in this case, I'm looking for the third row or the row that has value of 2. Make sense? Because the first and the last bit. So this one, I'm here. Okay, good. How can I identify which column? Take the rest in the middle here, which is going to show you which column that we need to navigate, check. Okay, so in this case, let's be back here, 1, 0, 1, 1. So 8, 4, 12, and 13, right? I need to find the column number 13. Or the 14th column, right? So intersection here is going to be here. What's the value? I made a mistake. I can't see the value. That's funny. It's new glasses and I'm still having an issue here. So anyway, I'm going to use the eraser just to see what's the value. Oh, 10. Good. You got it? So it's going to be 10 here. So result is going to be 10. How can you represent 10 into a binary representation? 10, that means this bit 1, this bit 0, 1 and 0. So the result is going to be 1, 0, 1, 0. This is the result after you perform that. Clear? The first and the last bit is going to just tell you which row, and the rest is going to identify which column that you need to investigate. I need to check. The intersection is going to be the value, then take this value and convert it to the binary representation and the result. So for every single bits here, you're going to produce 4. Every 6, you're going to produce 4. How? So here the first 6 bits is 1. The second, there is another table is 2. The third 6 bits, there is another table is a 3, and etc. All of them, they are different. The same structure. Give me a second. I will erase and do this one again. I confused you. So we'll start with the beginning. You have a message, okay? And the message, the input here is going to be what? 48 bits, right? You divide this one chunks. Each chunk has 6 bits. Clear? So the first 6 bits here, the second, the third, up to the last one. Makes sense so far, so good, right? For the first 6 bits, each 6 bits is going to be applied based on a specific substitution table in order to produce the result. So you have 6 bits at input, you apply this table, and they're going to produce 4 bits at output. Clear? Good. Let's have an example. How can you use? Assume that the first bit that you have has this number. I'm going to use this one, okay? To be clear here. 1, 0, 1, 0, 0, 1. Okay, you have 6 bits, and you need to apply the, let's say, this bit, let's say, substitution 1. That means we're gonna apply this table, the first table. Okay, how can I do that? In order this one, there is a way. They said the first and the last bit is gonna help you in order to use the table to lock up in this table. The first and the last bit is gonna identify which row you need to lock. With look at either the first or the second or the third or the last one. Clear? So the first and the last we have 1 1, right? What does that mean 1 1 in the decimal point? They are binary number, right? I need to put this one in the decimal. What's 1 1? 3, exactly. 3. That means go to the what? The in Sbox, go to the row number 3. That means I need to check the number 3. Clear? The rest of the bits here in the middle here help you to identify which column you look at. So we have 0, 1, 0, 0. This is, I mean, the binary. How can you put this one in the decimal? What's the value? It's gonna be 2. So that's me. Go to the column number 2. There's number 2. The intersection between 3 and 2 is gonna give me what? 0, 8. Right? So the result of S1 for 1, 0, 0, 1, 0, 1 is equal to value is, why is it 12? 0, 8. Why it's 12? Yeah, in the decimal. Yeah, good. So how I don't have 0, 8. So 0, 8 is going to be 4 bits, right? So in this one, I need to do what? I need to represent this one in the binary. How can you represent in the binary? 1, 0, 0, 0, right? In the binary. And I'll show you the way how to represent any numbers in decimal in the binary. Use this formula: to the power 1, to the power 2, to the power 3, to the power 4, and etc. So 1, 2, 4, 8. So in this case, this one bit is going to be 1, and this is going to be 0. The result is going to be 8. Right? And that's what we did. For every single 6 bit, you're going to do this one. I mean, every single, 6 bits. The first 6 with this one. The second 6 bits, you're going to use different table, different substitution table. Make sense? So we start with 48 bits. We're going to produce at the end 32 bits using these tables. I expect from you to know how to do that. So it might be choose the right answer, it might be true or false. I give you the S1, I give you, for example, what's the input value, and you have to tell me what's the output using this table. Okay? That's what I want from you. You don't need to memorize anything. The only thing you need to see, how could you look up in the table. Maybe confusing if you look at, you have a 4th row and the 3rd row, that's because the value here, okay? Just give me which column you need to access. So better to say, I mean, the first and the last bit is going to identify what's the actual number that I need to use in order to look up the table. Good. Hopefully makes sense, guys. The other one we have what here? We're going to take a look. The last step here, we have a permutation. Okay, so this substitution, and this is going to perform permutation. And the permutation, you're going to do something. We call this one, by the way, straightforward permutation here. What does that mean in this case? Because here just, I mean, we have what? I need just to have basically the table. I'm not going to remove any input. The only thing I need to change or permute the value within this table or within the plain text. Okay? Here, the permutation, we have only one single table. And this is the way which table we're going to use. This is this table. Okay? That's what I have here. Only one table. So that means in this case, it's going to map each input bit to an output position. There is no bits are used twice, and there is no bits are ignored. That's why we call this one straightforward. Okay? The good thing here, we're going to talk about something called avalanche effect. Okay? What does that mean here? The system said, okay, if you have one bit here, changed, one bit, if you change flip one bit, this one will end up, we have 2 bits going to be changed at the end. Yeah? Then after that, for each single one bit here, it's going to be changed, it's going to affect 2 other bits. and etc. You see that? That's why the effect is going to be changed. So that means the more rounds that we have, the more diffusion that we have and confusion. So avalanche here effect is defined as what, generally speaking, small change either in the plain text or let's say in the input, or the key should give you big change. Of course, after you perform what, multiple, let's say, iteration, going to be increased this one. One thing we can look at, if you single bit difference in each Sbox, and get a result to say change in at least 2 bits on output. So if you check here, for example, back here, if I change 1 bit here, I need to erase this one here. If you change 1 bit here, this is going to affect the change. It's going to change for the input. It's going to be changed at least 2 bits at the output. Let's give you a quick example here. So this is the input that we have, right? We have something like this. This is the input we have. Let me show you here. We use the input 100101 and produce this one 10008, right? That's what we did here. How about if we change 1 bit here? Let's change this one from 1 to 0. Let's see what the result will get. 100100, and we want to see what the outcome. So I change only 1 bit here. If you change 1 bit, you see the first and the last. So you have 10. 10 is going to be what, 2. That means you have to check here, right? The row number 2, and the rest is going to be, say, go to the row number what here, and number 2. That's again, right? The result is going to be what here? 14. This one is going to be what? 14, yeah? So 14, that means in this case 1, yeah, let's say 1, 2, 4, 8, sorry, 1, 1, 1, 0, right? Am I right? Yeah. You see that? You change 1 bit, affect at least the result. If you change 1 bit from 1 to 0, this one will change what? At least 2 bits at the outcome. That's another property that this Sbox is going to provide. Imagine you change 1 bit somehow on the high level. This one affects multiple bits. And each of these bits, again, is going to affect more bits at the end. You see that? And we do permutations. This one, this bit, or the changed bit, is going to be redistributed, or it is scrambled within the message. So we have a different position. And each of them, maybe it's going to change at least to another bit. You keep this after 5, 6 rounds, you figure out that maybe all the data is going to be completely, change 1 bit is going to affect at least half of the bits of the outcome on the ciphertext. Make sense? Please say yes. Thank you. By the way, today is a special day, right? 02/02/2022. Oh, that's great. Ah, that's great. Okay. So just, when what I'm doing here, if I said something, I need to convince you that there's a reason behind this one. So I didn't want to say changing 1 bit in the input, going to change at least 2 bits at the output. And you can test this one here. You see, you change only 1 bit. You see, if you change just one other thing, maybe you're going to change more. And remember, the permutation here, these bits 1, 1, 1, 0, is going to be spread and within the message. Then again, it's going to be input in the next iteration. These bits are going to be affect another one. So it looks like snowball, starts small, and with the time, it's going to be getting bigger and bigger and bigger. I hate snow. Why you came up with the snow example? I'm not a big fan of cold weather, yeah? In the summer, I'm the happiest one. I saw that most of the people are they're in the camps are struggling. Oh, it's too hot. For me, come on, it's nice weather, it's refreshing. Anyway, we done the permutation, then we do this one multiple times, and this is, the effect of Avalanche effect. So we end up, we have like huge, great, diffusion at the end of the system. Okay? We done with this one. So we do this one 16 times, or iteration. Now we need to look at the way of the key, just to give you an idea what kind of function you can use in order to produce the key. So I'm not going to say the interesting thing. The confusing part for this kind of, DS, the structure that we have or the algorithm that we have. they set the size of the key at the beginning 64. Then we're gonna remove the parity check 1 bit, the 8th, the 16, etc. bits, and up we have 56. So we never use 64. Actual key size of the DS is 56. Then after that we shrink this one to be 48. So that's the way at the beginning here. Your size of the key 64 bits here is reduced to the 56 bit, okay, key, by ignoring every 8th bit. So you have the 8, 16, and so they're gonna be removed. All right. So how can you do that? That's basic permutation choice. We have a special table. We're gonna use this one in order to help us. So we have a permutation choice 1 here. Permute. Take 64, reduce to the 56. Good. Based on this one. Done to this part. Then after that, after these, or the 56 bits is going to be extracted, we are going to have what? Generate the different 48 bits used as a subkey. So this is how. Just an idea. Of course, I'm not going to ask you the exams or how exactly going to be generated, but I give you like an idea. How can we generate a subkey using our single key? So we have only one key, 64. After the permutation choice, the first one is going to reduce to the 56, done with this one. Then the 56, now I need to have for every single round, I need to generate a key. This is the process here. You're going to perform here for every single round, okay? First, you need to divide this one into 2 halves, left and right, okay? Each of them is going to be what, 28 bits? Yeah, because we have 56, so it's going to be 28 bits, okay? Half. These halves, each of them is going to be shift left, and you call this one cyclic shift there. Okay, so you shift, we have 28 bits. You're going to shift this one to the left 1 bit, and the one is going to be filled down, is going to be added to the end. That's why you have a cyclic shift left. And the way that you have each part is going to be, or half is going to be shift by itself. I mean, so it looks like we have 2 parts here. Here we have this one, you have to shift this one alone, separately, and this one separately. Yeah, so whatever you're going to fill down here, or they're going to be back, left over from the, because you need to shift to the left, this bit is going to be back to the end here. And the same thing here. For each of them, some based on the round, some rounds you're going to shift this one by 2. And some round is going to be shifted by 2 bits. Or 2 bits, and some of them is going to be shifted by 1 bit. Okay? So at the end, we're going to end up, we have 28 shifts to the left. So at the end, whatever we have at the beginning, it's going to be here. Whatever C0 and D0 is going to be similar to the C16 and D16. I mean the content. Because here we have 16 rounds. For some rounds, we're going to shift this one by 2. Yeah. So actually, for 12 rounds, we're going to shift this one by 2 bits. So it looks like we have a 12 multiplied 2 equal 24. And we have 4 rounds, we're going to shift only by 1 bit to the left. So we end up, we have shifting after 16 rounds, we're going to shift the bit to the left, or rotate shift to the left, 28 by 28 bits. So we end up, we have what the input, at the end it's going to be similar to the output. I mean, I'm talking about the C0 and the content of the C16. And the D0 here with the content with the D16. Okay, clear? Once you do the shift here, for example, the round 1, we're going to shift only 1 to the left, here and here. Now we need to use permute choice 2, which in this case, again, we have 56. I need to reduce this one into have 48 bits. Okay? Using this formula. Good. One thing I need to add here, by the way, all these tables are fixed. Okay, we're not going to change them. They are fixed because this is the fixed table. This is the structure here. One thing I need to add, you are going to use all the keys that we're going to generate? No, not all of them. I mean, sorry. All the keys that can be valid keys? No, because remember we said we have what? 64 bits, the initial number of bits, the size of the key, right? Or the length of the key. If you have it, say, example here, just try to come up with a quick example here. Assume that we have 56 bits. This you have to go the initial size. I mean the actual size of the key. 56 bits. All of them gonna be zeros up to all of them gonna be ones, right? So we have 2 to the power 56 bits. I mean, sorry, keys. Alright? this whatever billion quadrillion, I think 7.2, whatever the size. It's a huge number of keys, possible keys. Do you think all of them are valid keys? No. For example, do you think if the key, all the bits are zeros or all the bits are one, are good choice for the key? No. So it looks like when you come up with any algorithm, you can say there's some kind or number of keys are not allowed to use for the security reason. Those I'm going to explain here. So we call this one weak key. That means in this case, when we use this one, or these weak keys, that makes the cyber algorithm that you have going to be vulnerable or maybe behave in some undesirable way. Give you an example. What's the weak key that we have in the DS algorithm? The weak key here, I give you the weak key with parity check bits. In other words, with the 64 bits, the size 64. Yeah, either gonna be have zeros and ones, okay, 0, 1, 0, 1, 0, 1, something like this, or maybe have F alternating F and D, something like this, or maybe you have E and zeros, and after that you have F and ones, alternating F and 1, or the opposite. Those are bad keys, weak keys. Don't use them. Why? If you use these keys, this one is gonna, remember that this is the master key. If you plug this one in order to key generation, in order to produce 16 keys, this weak key is gonna produce 16 identical subkeys. So all the subkeys from K1 up to K16 have the exact value. That's bad. We don't use them. It looks like they negate each other. So it looks like you thought that you're encrypting and you are not encrypting. Make sense? So there's some keys, we are ignore them. I want from you to be aware that not every single possible key you can use. The other thing here, by the way, when I say this one, either can be all zeros or all ones, or alternating zeros and ones. So that's why it's bad. So in this case, it depends whatever the input key that we have, it's going to produce, all of them are going to be identical, but what the actual value, either it's going to be all zeros or one or alternating 0 and 1. Okay? The second type of keys that we don't like, I call this one the semi-weak key. So there are what? This is not the difference between weak and the semi-weak key. The weak key is going to produce the identical 16 subkeys. This one, the semi-weak keys, is going to produce 2 different subkeys. So it looks like 8 similar, identical. Yeah? So 16, actually you have 2 different keys. It looks like we have only 2 subkeys. So it looks like in this case, each key is going to be used 8 times within the algorithm. So you thought that you have 16 unique keys or subkeys. Actually, you have only 2 unique keys. So 8 rounds, you're going to use the same key, and another rounds, you're going to use the other key. That's bad. We don't like this one. We do have another kind of third type of the key. We call this one possibly weak. This one is going to produce 4 subkeys, not 2 subkeys, 4 subkeys unique subkeys out of 16. So that's a bad idea. Maybe someone is going to say, okay, we're losing a lot of bad keys. Actually not. Because here, if you take a look, the total number of all these keys is going to be 48. And here we have, I think we have 16 plus 4, 48 plus 16 plus 4. We have 4 weak keys. We have 16 semi-weak keys. And we have 48 possibly weak. So if we take this one, and remember the total number of keys that we have to the power 56 minus, what do you say, 48. This is minus 16 minus 4. This one, do you know the numbers? I think I have it in this one somewhere. Let me check. Yeah, this one got produced 7.21 multiplied 10 to the power 16 quadrillion. Oh, so this one nothing. Yeah. So 99.99 keys are valid in this case. Makes sense? Decryption. In order to perform the decryption here, it's based on what? 5-star network. So that means here it's going to be almost similar, right? The same algorithm. The only thing that we need to do here, the way that how can we generate the subkey? We are going to use the subkey in reverse order. K16, K15 in the first round, K15 in the second round, and K1 in the last round, right? So in this case, the only thing we need to do here, maybe you have a minor change for what? For the key generation process. Okay? Remember what we said here. After perform 20, generate the entire keys, the C16, the last register value that you have equals C0, right? And the D16 gonna be equal to the C0 or D0, right? Let me go back here. Here, we said that the total number of rotation 28, right? So that means you start here with the specific value of C0. After you 16 round, you're gonna perform 28 shift left, cyclic shift left. So you end up, you have C0, and you end up, you have the same C0 at the end. So once you have this one, so this one gonna be the first one. In order, I will start from here in order to perform the decryption and then go up, right? To reverse the operation. I need to have whatever the content they have in the key here, because it's gonna be, it looks like I'm in the same value here, and just to perform the permutation choice 2 in order to produce the key 16 and go reverse the operation. The one thing that you need to be aware here for the key generation, instead you have shift to the left, you're going to shift to the right, or rotate to the right, reverse the operation. Okay? This is the only thing for the keys. How about the rest? It's going to be the exact thing. So in this case, the only difference when you perform the decryption here, the way that you're going to insert the key, or the way that you use the key here. Do you want to change something here? No, this one, the rest is going to be the exact thing. The only thing you have is going to be the ciphertext and do the exact operation here. So that's good, right? Because I can use the same piece of hardware in order to perform the operation. Yeah. Security. One thing here, when we talk about this, the initial and the last final permutation here, we said it doesn't, have anything related to the security purpose. Good. One thing, if you take a look at the security of the DS, okay? The simple thing here, you're gonna take a look here. The key space is too small, to the power 56. Based on the current computation, you can use your own computer in order to crack the system. At the time, yes, 20, 30 years, 40, 50, 60, 50 years actually ago, that's fine. But now the computation power getting increased, okay? So in this case, the size of the key is bad. It's too small. Why is bad? Because now for the user, we can perform what? As an attacker, you can elaborate every single possible key. You can come up to the power 56 possible key, one at a time, test, and you end up with finding the right key. Okay? And also the way that the Sbox design was critical. Most of the people, the work in the security or the cryptographer at the time said, okay, something suspicious. And they're right. I believe there's something wrong. Because the way that you design the system, no one knows why you choose them. After 15 years, they know that because there is another attack. So that's why use these the way that we design the Sbox like anti mechanism in order to mitigate this kind of effect or attack. Okay? Good. So since this, let's do the brute force attack. How can you do that? The simple thing, okay, you have the message, see? Okay, I do the size of key, it's 56. I can come up to the power 56, okay, K1 up to K to the power 56. And try to decrypt the message C and see what's the plain text that I got. Yes, I can do this one. Your computer can do that. So it's easy. You need to do what? To the power 56 possible. So how can you protect the system? The people said, okay, maybe using only once, you say depth of digital encryption standard is not enough. How about use double? How we have a multi or multiple encryption? Okay, so in this case, I can do what here? How about use double DS? What does that mean here? This means you have, for example, one DS, you have the message, okay? Then this is going to produce the ciphertext, yeah? And here maybe use K1. The outcome of the ciphertext, I'm going to use C1. I'm going to do another DS, another round, 60 rounds, using different key in order to produce the ciphertext. Can I do this one? Yes. Make it complicated. So we're going to perform this one. So each your encryption, you're going to perform 60 rounds, and this one 60 rounds. I use two different keys, two different master keys. Can I do this one? Yes. Or another thing is, how about using triple DS? So that means you take the message, okay, use K1, for example, or whatever key. Then after that, the output perform another 60 rounds, use maybe different key. Then after that, the outcome is going to perform another 60 rounds. Then this is the ciphertext. Terrible. Make it complicated. And we think that by doing this, maybe you're going to enhance the security. So we'll take this one, look at them, and see how can we attack. Okay? So we thought that if we use 3 different keys, this one, the security is going to be increased to 100, let's say 68, because to the power of 56 multiply 3. Okay? And this one, if I use 2 keys, maybe enhance the security to the power of 12. What does that mean here? That means you need to try 2 to the power of 12. How I got this number to the power of 56 multiply 2, because I'm using 2 keys. But I'm going to show you, no, this is not the case, actually. So this is the double encryption. Remember this DS 2 times. You're going to apply 16 rounds. Then after that, apply another 16 rounds with different keys. And this is the encryption and decryption. Assume that, let me write the encryption decryption functions. So here you have the plain text. You encrypt this one using what? Using the K1. Then the result is going to be encrypted using the K2, right? This is the ciphertext C. Okay, the intermediate result, we call this one X. Good. In order to, you have C reverse the order to get the value of P. Okay, how can you do that? So you take C, decrypting using what? Using the, the last one key that I use K2. I use K2 for the C in order to produce the value of X, right? I reach here. Then after that, decrypt the value of X using the K1 in order to hopefully get the value of P. So, in anyone who try to attack the system, try to find or do brute force attack, we said the security is going to be to the power, what? 112. To the power 2 multiply the size of the key. Alright? So that means that when anyone tries to attack the system, you have to perform to the power 12 iteration, tries, in order to find out the key. And I'm going to show you how. So the first, I do have K1, right? In order to, for example, you try to find out the key. Either start with the K1 or K2, okay? Assume that you have the plain text, you need to find out the corresponding ciphertext, or you have the ciphertext. Let's do this one. I do have the ciphertext, I need to come up with the plain text. So in this case, I need to decrypt the value of the C using K2. So in the K2, I have from K21 up to K2 to the power 2 to the 56, right? All the possible combination for the K2. Every time I need to decrypt the message C, and I'm gonna get X1, whatever the value of X1. Do this one to the power 56 times, end up to one, let's say, to the power 56 value here. Good? For each of them, I need to do what? I need to try decrypt using the K1. So for each of one here, I need to do the to the power 56 iteration or possible try using the K1. So that's why the total number of combinations, the total number of tries is going to be 2 to the power 56 multiplied 2 with 2 to the power 112 iterations or tries. This is how many operations the bad guy can do in order to attack the system. Alright? That's what we thought. But there's another kind of attack, or actually another shortcut. We have an attack called meet in the middle attack. That means someone is going to meet you in the middle. What does that mean exactly, this one? Let's take a look here. I noticed that it looks like either going to start with this direction or come with this direction. You're going to produce the value of X, right? In the middle. So what's the plan here? The plan here, I'm going to maybe try to perform to the power 56 multiplied by 2. So that's in the meet in middle attack. Let me do this one, the attack first. Let's do the attack first, and after that, see how it works. So here you have the message. If you take a look at the previous slide, you notice that the value of X is equal to what? It's going to be either encrypt, use the K1 for the P, or decrypt the K2 for the C. You're going to produce the same value of X, right? If you use the right keys. Let me get back here. You see that? The value of X either going to be encrypt using the K1 of P, or decrypt C using the key 2, right? So we're going to produce in the middle here. Make sense? Okay. So what I'm going to do here, I'm going to use this one in order to try to attack the system. So we're going to see, okay, this kind of meet in middle attack requires from you to have, 2 plain text ciphertext pairs. So assume that we have, for example, this is the one condition. We have PA and the corresponding ciphertext, and we have a PB and the corresponding ciphertext. So I have two pairs of plaintext ciphertext given. Okay, how can you do this one? First, you take the PA encrypting using the K1. All right. How many keys do you have in the K1? We have from, let's say, K1. I'm gonna use K1 and 1 up to K1, let's say, to the power 56. All right, for the PA. And this one produce different value of X. Clear? Are you agree with me? I do have to the power 56 possible key from sample key I can choose from the K1. Take the PA and encrypt it. It's gonna produce different values from X1 up to the power 56 value of X1. Right? Good. I did this one. Then after that, I'm gonna sort this one and put this one in the table. It looks like lookup table. So in this case, just to simplify the process, you can say the key 1 value and the X1. Sort them here. Just to help me. Good. Then what I'm gonna do here, I know that I will try, it looks like meet in middle attack. So I will try to find what? Try for using the K1 from one side to reach the value of X. Then I will try to reach the value of X using the value, different value of K2 until I find the correct value of X. So in this case, I'm done for this part, first one. Then I know that decryption K2 from C is going to produce somehow the same value of X. But if they use the right value of K1 and K2, all right? So take a look here. I have K2 and 1 up to K2 and to the power 56. We have all the possible combinations, but they are not related. I can't do this one in parallel. Okay? Then after that, you take for the value of CA, then in this up to the CA, this one is going to produce X1 up to X, let's say, to the power 56, right? For every single value of X that I produced, based on the K2, I will check in this table to see which there is a match or not. Definitely, if you use the right key, you're going to find a match. If I find the match, you're going to say, okay, I found the match here of the X1. What the key 1 value was at the time. I will mark the key value at the time, key 1, and I know, for example, the K2 value. I need to check. So it looks like those are the keys. How can I check them? I do have another pairs, right? For the P and CP, yes? So either I'm going to encrypt, for example, B, what they say, K1 that I found it here, yeah? And see whether, then after that, encrypt using the K2 that I found it here, and see whether it's going to produce CB or not. If they produce the same value CB, that's confirmation that I use the find all right key. Is it clear? Man in middle attack. You meet me in the middle. There's no need to start with the plain text and double the ciphertext. No, let's have it in the middle. So if you encrypt the plain text, you're gonna use whatever key and go to the other side, decrypt the ciphertext using the key value, key 2, definitely gonna meet in the middle. What's the last step? To confirm, you mean, right? The confirmation. Now we figure out, for example, yeah, okay. You assume that since the X1 here is equal to specific value X1 here. So you know the corresponding value key 2 and the corresponding value of K1, all right? Or here, but I put this one in the table just to speed up the lookup. So I have two keys. So I assume they say K1 and K2, okay? I need to check whether they are right or not. So you do have another pair, yeah? I can use this one in order to confirm whether my answer is correct or not. You have many ways to confirm. This one way, let's do the other way. I will take the CP, decrypting uses the K2 here. Then after that, decrypting uses the K1. And see whether I can use PP or not. Figure out. Or you take, for example, the plaintext P, okay? Encrypting use the K1. Then after that, the result is going to be encrypted use the K2. This one is going to produce, definitely, if you use the right key, it's going to produce the same ciphertext, which is going to be CP. Just another pair in order to confirm whether my answer makes sense or the keys are correct or not. Okay, so in this case, it looks like the time, how many operations you're going to perform here. In order to encrypt the X1 up to, let's say, PA to the power 56 times use the K1, I need to do to the power 56 operation. Here, not for every single key I need to perform operation. Here, this one to the power 56, separate operation at most, right? We can do this one parallel. So the result here to the power 56 plus to the power 56 end up to the power 57. So using the meet in middle attack, we prove that we have a shortcut. The security is not 2 to the power 12. No, the security can be I need only at worst case scenario to do to the power 57 operation in order to figure out the correct keys. So what's the difference to the power 56 and to the power 57? Nothing. So it looks like the security degraded. It looks like we're still using the single DS. So that's bad idea. Okay? And this is, I mean, the meet in middle attack, that explanation here. That's what I've said here. That's what I summarize here. We know, by the way, you need to have two known enemy plaintext cyber pairs. Succeed, it's going to be almost one. It's going to be almost close to one because you have two keys and you have another way to how to prove if you have another pair. Yeah. Of course, we need to have a computational complexity associated with this meet in middle attack. I need to have a space to store to the power 56 value of x1. Building the table, lookup, storage, etc. That's fine, it's acceptable. But at least the result here and being able to defeat the two double encryption. Okay? So again, we conclude that double encryption is not much more secure than single one. So what's the solution? The triple disk with the one that you used currently. We make it complicated. We're gonna do this one 3 different keys. We're gonna perform the DS 3 times because of meet in middle attack. We cannot do 2 times because it's not secure. Yeah? So in this case, this have a special structure, special design. So remember, we're gonna do DS 3 times for the encryption and decryption. I'm gonna do, since we have a DS, the first one you're gonna, in DS, when you perform DS encryption scheme, usually you have performed decryption or decryption, right? So the algorithm gonna say the first one, let's say come on. Okay, I'm gonna use 3 keys. Each of them 60 rounds, okay? This is the plain text, and this is the result, okay? In order to DS, I have a choice, either use encryption or decryption. The model that the structure looks like something like this. The first one, I'm gonna perform encryption. The second DS, I'm gonna perform decryption. And the third one, I'm gonna perform encryption. So it looks EDE for the encryption. In order to decrypt, you have to start from here, you reverse the operation. So to reverse this, you have to do the decryption, right? To reverse this, you have to use encryption. To reverse this, you have to use decryption. So the model is called EDE, encryption, decryption, encryption. Why they use this one? Why they came up with this model? This one because of what? Because we do have, it's allowed by doing encryption, decryption, encryption. If I have a piece of hardware that uses encryption, double disk based on this formula, we can implement it I can use this one for the single DS. It's like backwards compatibility. The same thing the Windows are doing. When you have a new version for Windows, it's keep tracking, you're still being able to use whatever files, especially for the Microsoft Office words, allow you to fetch, load or store, work with the old, document that produced by the old versions. Yeah. So in this case, if you have a piece of hardware, and the piece of hardware, generally speaking, gonna say, okay, give me the keys here, K1, K2, K3. Okay, and this is the plain text, and this is the ciphertext gonna be out. Inside this one, we have encryption, decryption, encryption. Yeah. So I can use this piece of hardware in order to perform single encryption because of still, for example, my software, my hardware that I have, I need to still be able to use single encryption scheme. That's the normal form. If I said both the K1 equal K2 equal K3, all of them equal the same value, so in this case, what you're doing here, if K1 and K2 are the same, this one is going to be eliminate the effect of each other. Then we're going to perform encryption, use the K3. And the same thing for the decryption. So I think, again, only for in order to provide backward compatibility with the DS. So that's why we use EDE. Okay. Another thing we need to look at, we have many variants of the keys. Either I'm going to put K1, K2, or set K1, K2, K3 to the same value. That means in this case, I'm going to use what? It's going to be single DS. Good. Another variation, I can use the key or two keys. What does that mean in this case? I do have K1, K2, and K3. I can use this one as, similar to the 2DS. Okay? How can you do that? That means in this case, I'm going to replace K1 with K3 with K1. So it looks like in this case, K1 equal K3, and K2 is going to be different. So I do using two different keys, only two keys. How can you do this one? You have to set K1 with K3 in the same value, and K2 different. So here we're going to use 2DS, if you want. And this one will provide 2 to the power 112, right? This is the key length, I mean. The third one, or the third variation, with the normal way how to use the 3DS. K1, K2, K3 are 3 different keys. They have 3 different values. Okay? Which, the way that we're going to work with here. This is the way. And you know that the encryption, decryption, when you encrypt the message, here you take out, for example, you take the message P, encrypt it first with the K1, right? Then after that, the result will be encrypted with the K2, decrypt with the K2. Then after that, the third one, which is you got to encrypt with the K3. In order to reverse the operation, first you have decrypt the K3. That's what we did here. Then after that, the result will be encrypting using the K2 to reverse the operation of the decryption with the K2. Then after that, we're going to do what? Decrypt with the K1 in order to produce the result. Can you do meet in middle attack? Yes. But the problem in this case, either going to meet in P or in A. Yeah? You cannot meet in A and B here. You cannot meet here at the same time. Either meet me here or here. So it looks like in this case, in one position, either I'm going to decrypt this one 2 times, or you're going to be encrypt this one 2 times. So in this case, when you perform the meet and middle attack, it requires from you to have 2 to the power 112. So that's why it's going to be more secure in this case. Make sense? That's all about the DS. Okay? We do have an animation. By the way, next lecture. I'm sorry. Yeah, I have to stop now. I know maybe I talked too much. Okay, the plan is supposed to finish this one. I'm gonna finish this one next lecture definitely. Then after that, I'm gonna talk about the lab. I'm going to assign the lab this week. Okay, lab 1, just you need to prepare your environment. Okay, you just install the virtual box. Then after that, we need to install, upload and install what's called, the Ubuntu version or virtual machine, which allow us in order to perform the labs. Okay, so I will assign this one maybe tomorrow. Send you email. Please, guys, try to do this one. Use your own machine. Everything can be protected. Yeah, definitely. This is the first one. You need to prepare, the environment. Then after that, we're gonna, once we finish the symmetric encryption scheme, we are going to practice all of these encryption schemes. Okay, we have lab 2, which is gonna be take care of the symmetric encryption scheme. Okay, thank you, guys. See you next week.